on Thursday, but before that, just sort of a recap of various announcements. On Thursday, I went over some of the details in the progress report. As a reminder, I think that's due next week, so the 30th. So next Tuesday. Because of that, you'll notice there'll be a new assignment today. That assignment won't be due till July 6th, so you have additional time, and the lab this week won't be due. Normally would be due next Monday, but that's being pushed off a bit, just so you don't have a bunch of stuff all at once, and you'll have some more time to work on it. We're also getting towards the end of sort of the really critical stuff. So Thursday's lecture will be on analog to digital converters. More or less at that point, hopefully you should know almost everything to get the robot sort of moving, reading sensors. If you have stuff you want more details on, I can sort of juggle around. Some of these later lectures are information that's useful for the design process, but you might not need directly in your robot. So I'll sort of ask afterwards if there's stuff that you want covered in more detail, you want more of a tutorial on. There's a lot of openings here to change that around to make it more useful. And in the lab today, we'll be talking about metal detectors. So you'll go through the design of a metal detector, which could be a useful sensor depending what you want in the robot course. And just as a reminder, so that progress report, hopefully we've started to at least think about it or do some outlines of it. It's directly worth quite a bit, 15% of the grade. And I went through, and you can see sort of the slides of the recording of the lecture, what it has to include. It's a maximum of 5 pages. Somewhere it says that. Where is it? Yeah, a maximum of 5 pages for the report itself, and up to 3 additional pages for additional information. And again, this was all in the original course outline as well, so this material has been repeated several places, but if you have questions specifically, or maybe I should ask that, are there questions on that progress report before we move on? Right now, you can ask later, but okay. If nothing specifically on that, and as I mentioned, the lab, so the lab, both the lab and the assignment will end up actually being due at the same time, but you're getting several extra days to finish the lab this week. This is the assignment. The lab, let me pull that open for you. Yeah, the lab. 4, lab 5, metal detector. So the lab, so rather than being due directly next week, it's a few extra days. And this one will be about metal detectors. So I'll talk about this towards the end, right before the lab. All right, so signal conditioning 2. What I'm going to cover today quickly, I'm going to recap filtering because it's such a critical section. I'll talk a little bit about LC tank circuits. This is what you'll experiment with in the lab. I'll explain a bit of the meaning of Q, which will sort of help you understand some of the work you're going to do in the lab, and talk about envelope detectors, which again are directly used in the lab. They will be useful for a few other sensors for you. All right, so recap of filters. There's more details in the lecture, either slides or the recording from last week. But very briefly, we have just a few types of filters. So low pass, high pass, band pass, or band stop. And all this means is the filters have some limit below which they don't pass, or they greatly attenuate certain frequencies. So what this means is that if you have a filter here, and this is 4 kilohertz, it's only going to allow frequencies below that to pass through. So if you apply this to a voice signal, you could attenuate higher pitched tones in your voice. If you applied it to music, maybe if you only want lower frequencies to pass through. Or in the terms of your robot, you might find this useful because, for example, you could have the high-pass filter where you have a light sensor, and what you have is at 60 hertz here, you might have a strong light source. And this is from incandescent light bulbs and other light bulbs or fluorescent light bulbs. which will give you a strong signal at either 60 hertz or sometimes double that at 120 hertz, depending on the specifics of the light. And this will be a very strong signal because the lights are designed to keep the gym very bright. But what you want to sense is some other signal way up here at, say, 500 hertz. This 500 hertz signal might be a little weaker. So the problem is that the 60 hertz signal would swamp your detection circuit. So what you can do is you could put a high-pass filter on, which will help eliminate that lower frequency noise. And you'll only see the 500 hertz or the 1 kilohertz or the 2 kilohertz signal. So this just requires you to design a filter that passes those higher frequencies and rejects those lower frequencies. To do that design process, and I don't think it's on the slide, you need to know, basically you need to specify first what requirements you have. So this includes things like what is the pass band and what they call the stop band. So the pass band is, in this frequency range here, I'm more or less allowing these frequencies through. So what this graph is showing is this is attenuation, which is a ratio of the, a ratio of the output voltage to the input voltage of the filter. So if we just look at it as a black box like this, we have V in, we have V out. And we could say, at 1 kilohertz, V in is equal to 1 volt, and V out is also equal to 1 volt, let's say. And then we could say, well, but at 10 kilohertz, again, we're using the same V in, so we're just going to sweep this input voltage across the frequencies. Maybe now V out is equal to 0.1 volts, so 100 millivolts. So we've attenuated, we would say, the output signal at that frequency. Rather than having to put when I put in this voltage, this is the output, we almost always use ratios. The filters themselves just will attenuate a signal by a certain factor. They typically aren't subtracting a voltage or anything like that. So you could say the output voltage V out over V in equals 1, so there'd be no attenuation. Or you could do the same thing here, V out over V in equals 0.1. So if you put in 5 volts, you get 500 millivolts out for that second example. So there's always this ratio of attenuation. Now the unit we use for this ratio is we like to express it not as a decimal like this. We use what are known as decibels. And a bell is just a logarithmic ratio. And you can calculate what a bell is by simply taking this ratio, so this V out over V in, and we simply do a log V out over V in. Bells themselves are designed for power, so we'll take the square of that. So we just square that ratio, we take the logarithm. This gives us a bell. When we're talking about decibels, it just means a 10 times improvement in it, or 10 times, not improvement, sorry, multiplication or factor. So this would be the dB ratio. Rather than having to do that square, what we can do is we can move the square outside of the log. And this is when it's dealing with voltage. So if we had power, if we said I put in 5 watts and it dissipated some of that power and 2 watts came out, we don't have to do the square. The square is only because we're talking about voltages. So what you'll see this written as is 20 log, because if they just get rid of the 2 times 10, they get rid of the square, and we can directly get a voltage ratio. So that's what the previous figure I was looking at was showing everything in decibels. And in this case, an attenuation of 0, if you have 0 dB, this is a ratio of 1. As we get to negative, the negative attenuation, it really should be the negative gain. We have ratios less than 1. So we can see a little figure here. Like if it says negative 10 dB, this would be this, this is a power ratio, so I need to multiply that by 20. But if we have a negative dB, you see that the ratio is below 1, meaning there's less output power than there was input. So on this figure here, what we're showing is that as the frequency increases, at some point in the stop band or what we call once we're in the stop band, it's very much attenuated. It's letting very little of that signal through. And so this is at the higher frequencies, it's letting a lot less signal through than at the lower frequencies. So you can define, how much do I need to suppress that signal? If I have a 1 hertz, or, again, let's say this is up here at, let's say 500 hertz, and that's where your signal is. And maybe you know that there's this strong interference at 10 kilohertz. And so you can ask the question, well, if I know there's a 10 kilohertz signal, how much do I need to reduce it to avoid interfering with my main signal? So you could say, well, I need to reduce it, 100 times or 1,000 times. And this allows you to convert that to decibels to figure out what that attenuation factor should be. So it depends a little. If you have a very strong interference, you need a lot of attenuation. If you just have a little, a very weak interference, you may still need to attenuate it, but you don't need as powerful a filter. You don't need to worry about the attenuation as much. So that's sort of the design process, is to decide on what is the frequencies I care about and how much do I need to suppress everything else. And as I mentioned before, you'll see these decibels everywhere. The only real thing, or one of the main things to worry about, is ensuring you look at, if we're talking about a voltage, so voltage out to voltage in or something like that, we have to use this 20 log. That 20 is because we squared the voltage to get a relationship to power. If there's a power aspect, so if it's I put in this many milliwatts, get out this many milliwatts, we use the 10 log of the ratio. So you'll see that far outside of this field as well, not just in electronics or not just in the filters. The simplest filters were the RC filters, and the assignment will have you doing a few of these. There's some online tools that help you design them. I linked them in the previous slides. I don't think I have the link in this slide. So when you go to do these calculations, you can just use those online tools. That's by far the best way to do it. And so the link's not in the assignment, but if you go back to the slides, they have all the online design systems, or you can use the equation directly and solve for, if you choose a capacitance, solve for a resistance. And the RC low and high pass, you can see the only difference is really how we switch around the resistor and capacitor. If you want to sort of have an intuitive feeling about this, what you can say is that a capacitor at DC is basically an open circuit. So at very low frequencies, like 0 hertz of DC, that capacitor is effectively removed from the circuit. So it's open, and all you have is a resistor. Because there's no load at all here, the output voltage, and therefore no current flowing, the output voltage is equal to the input voltage. So at low frequencies, output voltage is equal to input. At very high frequencies, so high frequencies, ERFs, HF, like kilohertz or megahertz, however you design it, it'll depend specifically. This capacitor acts as a dead short. Acts as dead short. So what you have is the output voltage will be around 0. And you can say the same thing if you want the intuitive feeling for the high pass filter. At high frequencies, very high frequencies, this capacitor will act as a dead short, meaning the output voltage will be equal to the input voltage. At very, very low frequencies, the capacitor acts as an open, so effectively is removed from the circuit entirely, and the output voltage is just pulled down with a resistor to 0, so you have 0 volts. And in between, it's some combination of them. And so this is what we see in the frequency graph, is at low frequencies, the output voltage, this negative is showing it's highly attenuated, so there's very little of the input voltage at the out. If the output was 0, it would be entirely attenuated. And as we increase in frequency, we get closer and closer to the input voltage at the output. All right, so the other thing you should sort of have heard about is SNR. SNR very briefly stands for signal to noise ratio. And the calculation of it is almost exactly as the name implies. It's simply the power in the signal divided by the power in the noise. So the signal to noise ratio is normally expressed in dB. And if you know from dB, we can use this exact same equation we had before. So if we have some signal, at 10 kilohertz, and we're going to claim right now that's entirely the noise. In reality, what you have is the noise is spread across a large bandwidth. But if we could say, we can easily measure just one bit of the noise. So, we are claiming this is easily known. Claiming easily known. And then the signal is normally easily known because you have some, this 1 hertz sine wave is our signal or something like that. So we can just take this ratio to get the signal to noise ratio in decibels. So if the SNR is positive in decibels, it means there's more signal than there is noise. If it's negative, it means there'd be more noise than signal. So this is how we sort of define how strong the signal is that we're attempting to receive. So they use this a lot in radio communications. You'll find receivers that are very, very sensitive can have a negative signal to noise ratio, which means there's more noise than there is signal. So things like GPS receivers work down at, I forget the exact spec, but it's a very, very small signal to noise ratio. And they do a lot of processing to basically pull this extraordinarily weak signal out of a huge amount of noise. And if you were doing stuff like measuring, again, if we were measuring power, you just have to remember it's this 10 log instead. So power would be in RF. For what we're doing, it'll probably mostly be in volts. All right, so that's the very brief sort of overview of the SNR. That's all you need to know. That information is also repeated in the assignment. So all you have to remember is that the signal to noise ratio is telling you to use the signal and the noise, form a ratio like that, and convert it to decibels. So it's almost exactly as the name would suggest. So I talked a little bit on Thursday about active devices, or op amps in particular. The first thing we saw was the op amp buffer. So the op amp buffer is a very simple circuit where we have the input voltage here. So if you have 1 volt in, you get 1 volt out. And it just replicates the voltage. Why the op amp buffer is nice is that it doesn't load your circuit, and it can drive a very strong signal at the output. So you can use this if you have a very weak sensor that you want to interface to the AVR. You can use a buffer like this to avoid, having negative effects in the sensor. Or if you want to add a filter to a sensor, the filter itself will add, if we go back to the filter circuits, like a simple low-pass filter. The problem is that as the frequency increases, I mentioned, at very high frequencies, that's effectively a short. And in between, it could add a considerable load to your circuit. So if you have something like the, a phototransistor here, and the phototransistor has, a 10K resistor, for example, and you're trying to filter it, what's going to happen is that this circuit might load your phototransistor and give you sort of incorrect or not as sensitive readings as it could be. So the simplest thing to do would be to add a buffer in there. So add that op amp buffer circuit I showed you. And now it's isolated the filter from the photodiode or phototransistor. The other thing we can do, and that's what I covered on Thursday, I won't go through the detail again, is that you can actually design filters using the op amp. So you integrate the op amp into the filter circuit. And again, there's really good online tools to help you with that design process. The other thing we can do that I didn't cover Thursday is just directly amplify a signal. So no filtering involved. But what we want is, if we have that's later. If we have a signal like a small little waveform as an input, maybe that's only 100 millivolts in amplitude, and we want a bigger signal that we can send to the AVR or do something else with. So all we do is the amplifier simply multiplies that signal by some gain. And so the gain is set through these two resistors, this RF and RG. So to use this, you would often just set one of them. You would say, well, I'm going to just pick a 1K here. And based on that, what do I need RF to be? So if I want a gain, and of course you're limited to physical resistor values. It'll depend a bit on what you require specifically, or you can make this resistor variable. So you have a few small potentiometers in your kits, and you could say, I have this sensor, I'm just going to tune this a little bit. And so, for example, if you wanted a gain of 10, you would then solve for what you want RF to be. If you're using just fixed resistors, you'd be more limited. So you may, for example, pick RF as 10K and say, well, I end up with a gain of 11. I wanted the gain of 10, but that's close enough. It works for what I'm doing. Or you could use the variable resistor to tune that to the exact gain you require. So the amplifier, how they work, just to give you a bit of a feel for where that equation comes from, is that all you have to remember about an op-amp is that it is attempting to make the positive and negative have no voltage difference, so at the same potential. And what the op-amp does is it controls the V out pin to accomplish that goal. And in effect, it sort of compensates for whatever you put in between the connection between the V out and the negative or positive, depending if you want inverting or not, output. So in this example, say you put 2 volts at V in here. The op-amp knows that this point has to be 2 volts. But what you've done is you've added these resistors here, which effectively divide down as a resistive divider in between the output voltage and that point there. So if we had, if we had this equal to 10K and this equal to 1K, in order to get this voltage to 2 volts at this node here, so again, because the negative node needs to be 2 volts, this node needs to be 2 volts. So you can just solve a simple circuit here. This is 1K, this is 10K. V out, and this point here is 2 volts. So if that point there is 2 volts, you can say, well, what's the current flowing through this entire system, or through the lower part of the resistor here? So you should end up with, what's that, 2 milliamps flowing? So there's 2 milliamps flowing here, meaning that the voltage across that top resistor would have to be 20 volts. So you end up with a V out equals 22 volts. And this is where that gain, if the amplifier can generate 22 volts, this is where that gain of 11 would come from. So all you have to remember about an op-amp is that it's attempting to make these two, the positive and negative terminal, have the same potential. Once you have that, you can sort of recover all the other information you need. So in this case, you can see where that gain figure comes from in the op-amp circuit. The other thing we can use the op-amp for is we could sort of, if you took this to the absolute extreme, and you use an op-amp in what's called open loop gain, it has a huge amount of gain. So if you don't have these feedback resistors at all, if these are just not connected, again, the op-amp is trying to make those two voltages the same, but it actually isn't able to control the negative voltage. There's no relationship between V out and the negative pin because you don't have it connected to something. In which case, what we'll get is we'll get a situation where the op amp is going to be switching between extremes. So it's either going to be going to the most positive rail or the most negative rail at the output. And what this will correspond to, so this is positive rail, negative rail. This will correspond to the point where one of the op amp's inputs is passing a reference voltage. So if we go back to before, we had the situation where the positive was V in and the negative was the controlled voltage. So if we have the signal here, we can put a reference voltage in at the negative instead. And all we'll see at the output of the op amp is a very strong signal indicating is the signal above or below this reference voltage. So this is really convenient because you might have a situation where you have, you know, the light sensor, for example. You don't necessarily care in the AVR about the absolute magnitude. You just want to know, is there a strong light present or not? In this case, you can then convert that, you know, that analog value into a nice digital signal, and you can very carefully set the threshold for at what point do we consider this on or off. In your kit, you have these LM339 chips, so you can ignore, I think it has the 139 part number, you can ignore that. It's the same thing. All it is there's a reference voltage, again, is the negative. So this is just an op amp. It's the same as an op amp chip. A few small changes in the actual design of the system to work better as a comparator. But this VREF, for example, you could attach to, you have these variable resistors, and you could attach this to, you know, plus 5 volts and 0 volts. And you could just tune, you could say, you know, I'm going to adjust the reference voltage, at which point it switches between on and off. And VN comes from your sensor or something else. These inputs, of course, are fairly high impedance, so they won't load down your sensor or anything like that. The only sort of trick with the LM339 or 139 in specific is the output is what's called something, it's called open collector. So at the output, you know, back here, I was showing it switching, you know, the voltage is plus 5 volts or 0 volts. These outputs are basically just a transistor, and you'll see why it's called open collector in a second here. So this is the output of the device, and this comes from, you know, the comparator logic, so you don't care about what that is. But all it can do is clamp the output to ground. It has no way to make the output a positive voltage. So what you have to do externally is add a resistor, and, you know, whatever value, like 1K or 3.3K, something like that. Depends how fast you want it to switch. For what you're doing, it probably won't matter. You could experiment a bit. And so what this will mean is if this is off, the pin will be at VCC. When the comparator turns on, it's going to bring it down to 0, and you'll get 0 volts at the output. So that's sort of the only caveat when you're using these LM339 devices that are in your kit specifically. Yep. So you just need the pull-up resistor. And in the lab, I guess I don't think you'll have to use the LM339 in the lab, but it's a good example because in the lab what we'll have is you'll make a metal detector. There'll be some voltage above which you're claiming you're detecting metal, below which there's no metal. And that's a really easy way to have that interface. The reason they sort of do this type of output voltage is that one of the problems we talked about with an op amp is you might have a situation where you have the op amp or the comparator or whatever it is, and the plus voltage, you know, you're connecting right to your battery. Because you have a very large, you know, you want your input voltage to be as wide as possible because your sensor can generate very high voltages. The AVR itself is powered from 5 volts and ground. So the input to the AVR can only go 0 to 5 volts to blow it up. So rather than having to deal with any sort of level conversion, all you do is you connect the pull-up here So if I say 1K, again, this value isn't too specific to 5 volts. It means the high level is now always just 5 volts, or it could be 3 volts if you're using a lower power device. Remember, all this device here can only pull to ground. It has no ability to push it up to that 10 volt limit. So you never have to worry that the LM339 is going to blow up your AVR output, as long as you connect the pull-up resistor to the AVR 5 volt supply. So that's sort of the reason why, or one of the reasons they do that, and how you can use it in your design to help have a safer system. All right, how are we doing? So one of the other tricks with the op amp, and you'll sort of play with this in the assignment through the simulator, is that, I showed before the gain just means the input voltage is multiplied. The output voltage is multiplied by the input by some, constant gain amount. And if we had a really simple signal that's around 0 volts, that's going from -1 volt to +1 volt, say, it works more or less as you expected. Let's say A is 1.5. It would now go from -1.5 to +1.5. The problem specifically for you, is you might not have an ability to use a negative voltage because you don't have a negative power supply. And so what will happen is, say your signal now goes from 1 volts to 2 volts, so it's the same 2 volt swing, or in this case it's a 1 volt swing, sorry, so the previous example should be -0.5 to 0.5. But it goes from 1 volts to 2 volts, so it's no longer around the 0 volt level. That multiplication will also shift the DC offset. So we still have that same 1 volt, and 2 volt level, and this middle part here is at 1.5 volts. But everything's going to be multiplied by the gain. So if the gain was 2, the DC offset would be shifted to 3 volts, which you probably don't want. You wanted it to stay at some lower level to feed into the AVR. So what we use is a virtual ground. So what a virtual ground means is I'm going to design a circuit where 1.5 volts is the null voltage. So that is the ground voltage. So what I would get instead is I won't get this shift upwards. It's going to remain around 1.5 volts, but the amplitude will be increased. And in an equation, you can consider that the output voltage is this Vn voltage minus the V ground, so the virtual ground. And we call it a virtual ground because it's not at a 0 volt level, but we're making the circuit behave as if that was the 0 volt level. So we're making the amplification around it symmetric. We're not shifting the offset voltage. And this is very easily done. So in the previous amplifier circuit, this was grounded. So that's sort of the classic amplifier. If I just set that V ground pin, the amplifier will now make everything symmetric around whatever this virtual ground voltage is. So this is very convenient in your system because, for example, the amplifier itself, is connected to, say, 0 volts and 7 volts. You can now make a virtual ground halfway between those points at, say, 3.5 volts and still get a few volts of swing on each side of that virtual ground. Without that virtual ground, you're going to be very limited in your ability to amplify signals effectively. And the reason is that if you don't use the virtual ground, if you want 100 times amplification, so say you have a 10 millivolt signal running on top of 1.5 volt offset, if you try to feed that through an amplifier with 100 times gain, this 1.5 volts would go up to 150 volts. So which isn't going to happen. It doesn't have that ability. And that's because you want that 10 millivolt, if this was just 10 millivolts here it's a little bigger, to be multiplied by 100 times you're only ending up with a 1 volt signal. So that the signal swing is fine, it's the offset that's killing you. If instead you set a virtual ground at 1.5 volts, you won't have that shift, and you don't have that problem. So to do that, all you would have to do is set this to 1.5 volts, and then your problem goes away. As I noted, there's an issue with the headroom on the amplifier. So the headroom is what we're calling, we have the amplifier itself. It's powered by 0 volts and say 7 volts. The output of the amplifier has limits on how close it can go. So it actually cannot go in these cheaper amplifiers all the way to 0 volts. You need what's known as a rail-to-rail amplifier to do that, to go from 0 to 7 volts or 0 to 5 volts. Instead, the output signal, so if you try to go all the way to the rails, what you'll see, what you want to see is a signal like this. And say it's going from 0 volts to 7 volts. What you actually see, so we have 0 volts, we have 7 volts, is a signal that sort of stops. So it has some clipping, and this is typically a few volts. It depends on the specific chip, but 1 to 2 volts below the rail. So this means that your signal can only swing from 2 volts to say 5 volts. So what this means is you need to work within that area of the amplifier output. So instead of having the signal swinging all the way from 0 volts to 7 volts, you need to deal with a signal that can only ever swing from 2 to 5 volts or something like that. And this is where that virtual ground is going to come into play. And so we can chain together amplifier circuits as needed to accomplish our goal. So in this example, what I'm showing you here is an amplifier circuit where I have a sine wave. So this is a 20 millivolt sine wave, and it's right around the 0 volt level. The 0 volt level is no good for us because we have this issue that our amplifier can't swing all the way to 0 volts. So we do a few things here. The first thing we do is we create a virtual ground. And how do we do that? We do that with just a simple resistive voltage divider. Now the problem with a resistive voltage divider is it's not what we would call very stiff. If we try to draw a lot of current out of that voltage divider, it's going to change the voltage, which we don't want. So this is simply a buffer, so a 1-to-1 buffer. So the input voltage is equal to the output voltage. So now we have a voltage source, that virtual ground, that we can draw a little bit of current from and not have to worry about it changing anything. We then have an amplifier here. So this is just that amplifier circuit with a gain of, and you can see it's 100K to 1K. So if you remember from the amplifier occasion, it's equal to 100K over 1K plus 1 equals 101. So here we have a gain of 101, which without the virtual ground, we could run into issues that it's changing the offset too much. The final thing we need to do is we need to shift this 20 millivolt signal that's right around 0 volts. We need to shift it up to the virtual ground point. Remember, what we're calling our ground is no longer 0 volts. And we do this with two things. We have a capacitor here. So this is, I think I talked about on Thursday very briefly the idea of AC coupling. So we're getting rid of the DC level on the signal. So this is what's known as AC coupling the signal. And finally, I have a resistor here. And this is sort of providing what you could call the bias voltage. This is shifting it to that virtual ground point. And finally, at the output, I'm in this case doing what's called an envelope detector, which we'll talk about in just a few slides. But basically, I've chained on another circuit at the output to give me something like maybe I want to just measure the amplitude of the signal. But we can chain a whole bunch of circuits together in this manner. And this type of circuit is probably pretty similar to what you can expect to see in your design. You're going to create the virtual ground, you might have to do this DC coupling, you might have to do an amplifier stage. Maybe you'll also need a filtering stage. There's no filters at all in this. Or this envelope detection. So this is sort of a rough idea of all the different things you might require. And actually, I'll come back to tanks in a second because I'll talk about that envelope detector. So at the end of that previous example, I had an envelope detector. So an envelope detector is just, if we have this black signal here, in red, we've drawn the envelope on top of it. So the envelope is simply, what is the maximum voltage of that signal. We don't care about, there's a higher frequency signal underneath it. We don't care about that. We're just trying to recover what was the amplitude of it. So in your robot, as a very simple example, we have this, you have this light source that's, 1 kilohertz light source. If you wanted to be very clever, you could try to detect what are the different frequencies. Can I detect a 1 kilohertz, a 500 hertz light? If you want a simpler solution, what you can do is you just have your light detector, and you might want to filter it. So this is what I talked about before. So I'm going to have a high pass filter. So what I talked about before was that there's this 120 hertz or this DC light source that could be very strong. We can throw that away. At this point, we could be left with, we could have a 500 hertz signal, we could have a 1 kilohertz signal, or a 2 kilohertz signal, or other frequencies. It could be, some other high frequency light source. But you might not care what the frequency is. So what an envelope detector would do, so you could take that envelope detector, is going to just tell you, what is this amplitude of the signal. Even if it's a very complicated signal, that goes up and down, typically the envelope detector will just give you this sort of maximum value. So it would just give you a rough idea of what the brightness of that light source is, regardless of frequency. The simplest envelope detector uses a diode and capacitor. So how this works is that, as you remember, a diode only conducts when, if I call this V1, V2, or A and C for anode and cathode, it's even better. So if the anode is more positive than the cathode, it typically has to be more positive by some small voltage, like 0.7 volts, so watch out for that. But if it is, it conducts. So for example, if you have 1 volt here, and we're going to ignore that conduction voltage right now, what's going to happen is that there'll be 1 volt here. Now if this input voltage fell, so if it went to 0 volts or 0.5 volts, I'll put 0, it's no longer conducting current. And the voltage is going to stay on that capacitor. The voltage on this side is going to remain at 1 volt because of the capacitor. If it was an ideal circuit, it would remain at 1 volts forever. It would never fall off. So that sort of ideal circuit, if I had an input waveform like this, let's go higher, what we would see, just change my color. What we would see at the envelope detector is whatever the peak voltage is, it would just keep. And as soon as there was a higher voltage over here, it would go up and then just stay that way forever. We probably don't want it to forever remain high, so they add a resistor which slowly drains the capacitor, in which case what you get is something like, oops, let me redraw that. So if you have that signal, if you have a resistor and capacitor there, you can tune how fast you want this constant to be, but basically there's a positive, and it'll slowly drain down, so it slowly goes down. The idea being that it doesn't forever track, what was the absolute maximum voltage ever. So if you wait long enough, it's going to go back down to 0, and assuming that becomes the 0 voltage. So this blue line is then the output of our envelope detector. But we don't have to worry about if there's a very high frequency or what that frequency is. And let's see, okay. And I'm going to run through how the simulator works, but before that, the other thing you'll see in the lab is what's called a tank circuit. So a tank circuit has an inductor and capacitor in it. These circuits have some resonance frequency, which is, and that can be very finely tuned. So the idea is that at the resonance frequency, it can present a very high impedance to your input. The objective being that if I excite this circuit at resonance, a very high voltage can develop in it because it's effectively oscillating. Any frequency off of that resonant, it won't develop as high a voltage across. So how you're going to use this is you're actually going to use this to detect small variations in the inductance. And those small variations happen when metal is brought near it. So you can excite it with a certain frequency. At that frequency, you'll get a strong signal. If you were to move the frequency, the signal dies off, or if the inductance changes. So in your case, you excite it at a fixed frequency, you change the inductance by bringing metal through, and you can detect a change in voltage. So I'll simulate it, for example, that exact circuit here. We can do this simulation where we see at some frequency, like, I don't know, 180 hertz or something. I don't know what it is exactly. We see this huge spike. So the solid line is this is effectively the attenuation. And we can see there's this large spike is at one narrow frequency. The circuit the voltage is spiking way up. So you can either choose to excite the circuit at this frequency and measure the voltage and watch it drop down, or you could even excite it, off the frequency such that when metal gets near, there's a huge voltage spike. But the idea is there's this one narrow frequency that has a very distinct response, and that depends on the inductor and the capacitor. How narrow that frequency is called the Q factor. So a very high Q factor is, and the Q factor is defined, is defined as we have what's called the bandwidth, which is the lower, this F1 and F2 is, the lower and higher limits at what frequency the device gets that large spike for. And we call that the delta F. F2 minus F1. So if we have a very high Q factor, it means that delta F is very small. So we divide by delta F. If we have a small Q factor, it means that delta F is very wide. Really what this means is that if you have a very, very high Q factor, that in the previous graph here, we have a very powerful, very narrow sort of spike that goes way up. If we had a very low Q factor, what that would look like, I would expect it to look something like this. So we have sort of a less well-defined spike in frequency and a much wider range it's over. So the advantage of a high Q factor is that it makes it extremely easy to detect the variations. The disadvantage is that everything is extremely sensitive then. So you need your oscillator running at just the right frequency or the circuit won't work. So there's a bit of a trade-off between too low and too high a Q factor. And I talked about envelope detector, so let's see a simulation of that. So in the assignment, I take you through, or I ask you to use the simulator. There is a video I made showing this. So if you haven't used LT Spice, just a simple example. It's free. You can get it for Windows and Mac. So you just make a circuit here, and we can do a tank. We'll do a tank circuit first. So you can place inductors and capacitors. Again, the video goes through all of this. And just wire them together. And the voltage source, there's this sort of, it looks like an AND gate, but it's actually a component library, so this is all the other components you might want on it. It has various comparators. You can add additional parts to the tool. By default, it has parts from Linear Technology, so you can look through all of them. But all we want is a voltage source. So this voltage source can be a DC source or sine wave or anything like that. And I'm also going to add a resistor to it. So if we add this here. And the only other thing, the one thing you have to be careful of is you always need a ground. So there's this ground symbol. And what this will do is just give it a 0-volt reference point. And finally, we need values in anything. So values, so this we're going to make a sine wave to start with. You can say 0 volts offset, so at what point in the y-axis, 1 volt amplitude, and say 100 hertz. And I'll use those same values, so 10, I think microfarads, was it? $10 microfarads and so that the previous photo had those backwards. So 10 microfarads and 100 millihenries. And 100 millihenries. So be careful of the micro or milli. Milli being 1 times 10 to the minus 3, micro being minus 6. And the resistor, I'll put like 100 ohms. And so you can just simulate this to get a time domain waveform, and you have to pick, how many seconds do I want to simulate for. You can just hit 1. You can put, 100 milliseconds or something like that if you don't want very long. And then you can click somewhere and get a simulation of the waveform. So this is our 1 volt signal, and we could look at the top of this tank circuit. So in this case, the waveform has attenuated a tiny bit. So what we're curious about is the frequency domain response. And so to do that, we switch our voltage source to what it calls, DC voltage. Really, we put in this placeholder, this AC1 placeholder allows the software to control the voltage and insert stimulus, insert the frequency of choice. And to do this, we use this AC analysis tab. And we'll say how many points do you want to simulate and what frequency range. So let's say 1 to 10 kilohertz. And it gives you, I had to place on the figure what it calls the simulation command, so that just tells it the information. And we can run the simulation. And again, I'm going to click at this point and say plot the, plot the attenuation for different frequencies. So you can see that it's this very sort of narrow graph here that's sort of showing you what the Q factor is. Or what it looks like, this would be a lower Q factor. And we can see that, right at resonance, it's almost like that resistor and capacitor, well, they are effectively removed because there's 0 dB of attenuation, meaning the output voltage is equal to the input voltage. Down here at 1 hertz, there's minus 44 dB of attenuation. So it's been reduced a huge amount. And again, at higher frequencies, it's also been reduced a huge amount. So that's sort of how the tank circuit operates, and we could see, the current through the capacitor instead. And you can see at low frequencies, no current flows through the capacitors, and there's some point where it begins to flow through, and the inductor should be sort of the opposite. So you can see right where they trade off. The blue is sort of hard to see, is where the resonant frequency is. And you can do the same. And you can simulate all sorts of stuff. So you can simulate the, if you want to see how the envelope detector works, do the same thing. And in this case, we're just going to do a solid sine wave, 1 kilohertz. And we'll just put a diode here. So this is it's quite useful if you want to have an idea for how your circuit should be operating before you build them and spend a lot of time, as well as testing values and easily doing the frequency sweep. So I'll put this as 1K and this is 100 nanofarads. And it does have models if you want to pick a diode, so the 1N4148 that's in your kit. And in this case, it's still set to that frequency sweep, so you have to remember to change the simulation command. And we can see, so this is the input waveform. And so in this case, what you can see in blue, let me zoom in here. Because I only have this 1K resistor, I don't know if you can see the blue very well. So this is the waveform on the output of the diode. So you notice one thing is that the input was this 1 volt, went up to 1 volt in amplitude. But because, remember, the diode has this voltage drop, the output voltage only ever goes up to like 0.4 volts because it had about a 0.6 to 0.7 volt drop. We also see that it's not really tracking what the amplitude is, and that's because our resistor is way too small. So I'm going to put like 100K here. And the specifics of the resistor, our resistor and capacitor have a time constant that you can calculate what a proper value would be, but just to give you an idea. So now you can see that the output of the capacitor is falling much slower. So it's doing a better job of tracking what the envelope is. Again, with that, always that 0.7 volt drop because of the diode. So if we change this to like 10 volts, we still have the same magnitude of drop, that point some volts. As a percentage, it looks a lot smaller. It's sort of hard to see the blue because of the fact that our input voltage is now 10 volts. So it's useful to do this. Maybe you can amplify first and then do the envelope detection if you're dealing with a weak signal. But you can see that it gives you a great idea about what the actual amplitude of that signal is, without having to do any further processing. So that's sort of all the material you should need. Where is it? The only other sort of reminder that I talked about, and I just want to emphasize, is that be careful if you are feeding from an op amp into the AVR, be careful of what the output voltages can be. Your op amp, it's more than possible, can generate higher voltages. The output here, if you had a 7 volts, or maybe if you had 10 volts, especially if you're using the power supply, this could easily go up to 8 volts at the output. So when it's doing the amplification, or if it swings to the rail, that will destroy your AVR chip if you don't have any protection. So what you can do instead is use a diode, and this diode will start conducting when this point is about 5.6 volts, or 0.6 volts above the AVR power rail, or 0.6 or 0.7. But this will keep it within spec for the AVR. So this will mean it'll limit the maximum value to your AVR and won't blow it up. You also would have a small resistor. I'm showing 1K here. You could do like 330 ohms if you want, or 3.3K. It depends a little bit on what you're doing with the signal. But what this is doing is limiting current through that diode. Otherwise, the diode can burn out and then it'll stop protecting the AVR. Or if you had enough current, you could actually introduce voltage transients or pull up the voltage on the AVR power supply. All bad things. So the current limiting diode will keep everything safe. So that's just something you'll need to use, especially in the circuit you do today. With the tank circuit, you may see some higher voltages on the circuit. Yeah, so today basically there was a recap of the filter material. If you weren't here in the lecture on Thursday or didn't look at the slides, you should see that for more details, especially the links to the design tools you'll need for the assignment and parts of your robot. We introduced the tank circuit that you'll see in the lab. So the lab's posted now, as well as more details of the op-amp. Before we go to the lab, any questions on this or other material or things? Okay, I'll put these up front, so pick up an assignment on your way out.